All right. Welcome to United Astronomy Clubs of New Jersey here in Hope, New Jersey. Uh, so, since I do see a couple people who are probably going to be wandering down shortly, they look like they're getting off the rock, or maybe they're just getting more comfortable. Welcome. So, we are live streaming this on YouTube and Twitch. So, if you're ever out and about and looking for something to do on a rainy day and you haven't managed to come here, you could always join us online. Hi, online chat. Um, so all our past all our past presentations, we also keep on our YouTube channel. So if you look at our website, uacnj.org, where you find a list of all of those talks, and you see one, man, I wish I hadn't missed that, you can actually go back and see it. And if you have any questions, feel free to put those questions down in the comments. I do try and scroll through and look for them periodically. And also, easy thing to do, hit those like and subscribe buttons. In addition, like I said, on our website, we also have a list of all our member clubs, because that is right, we are a club made up of other clubs, and our goal is to try and get science and astronomy to as many people as possible. And one of the best ways to do it is to find your local astronomy club. So if you're looking for a club, feel free to go check out our list to find the club near you. In addition, we also have our social media, Facebook, Instagram. We have a Discord channel for all the younger people. If you want to brag about, hey, I just got a new telescope, or you have questions because you just got a new telescope, it's a great place to ask questions and get those answered. So, since it looks like most of the people have wandered down here, you guys who are here get the safety briefing. It is inescapable. I will also give it at the end of the talk, just in case people sneak in. So, first of all, if you need to use the restroom, that is the porta potty in the back to my left, your right. It is illuminated by red to make it easy to find in the dark, and also because it's kind of dark in there at the dark. We also have a little museum and gift shop area to the door to my left, outlined in red. After the presentation, I will be behind the little gift shop desk because unfortunately I can't be in two places at once. So, until they allow me to clone myself or get that two places in one technology going, you have to wait a little bit. Not too long. In addition, when we are going to leave, we are using our headlights. We do not like getting run over. We do not like seeing people get run over. We do not like the paperwork or medical bills from getting run over. So let's avoid that. At the same time, as we're wandering around in the dark, because it does get dark in the state park, you do need to, if you have flashlights or like a cell phone light, try and keep those pointed towards the ground so we don't accidentally blind people because we're having flashlight raves. We like to enjoy our night vision. It makes getting around in the dark a lot easier. So not having those 10,000 lumen flashlights in your eyes really does help that feature. So I will throw the link in the chat once I get through intro. So tonight's presentation is, I was really hoping I would be able to turn and just be like, ta-da! The Beauty and Power of the Universe with Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in I can't read my own writing. 1985, just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and the Rockland Astronomy Club, and he's been volunteering here at Jenny Jump for over 20 years, which is really impressive. I hear 25 years, you get a cool pen. Maybe. I don't know. That used to be a thing, I think. Anyhow, here is Walt.
Okay. Yeah, as long as they don't try to give me a gold watch. I don't want to win any of that stuff. Thanks a lot for coming out. And I think you might even get a night of observing tonight, which is fantastic. I've started to to get a complex because every time I came up here, it would either rain or thunderstorm. I just went up to Vermont last week, and it was an entire week of rain. I didn't get to take a single astro photo, but I had a great time with my grandkids. Tonight, I want to be a tour guide, and I want to just take you through a bunch of different objects, different classifications of objects, both in the solar system and the galaxy and the universe at large. My only criteria was for selecting an object to show you was it had to either be beautiful, powerful, or even better, both. And the thing about the universe, though, is when I looked out there, just about every object out there is either beautiful, powerful, or both. So I got to just pick what I felt like talking about. One other thing I'm going to do, take you time traveling. Does anyone know how I can say that I'm going to take you time traveling? Excuse me? Exactly, light years. This is a picture that the Hubble took quite a while ago. Pillars of creation in the Eagle Nebula. And it's called the Pillars of Creation because new stars are being born there all the time. They're blinking into existence. It's located at a distance of 5,700 light years. So what does that mean? That means it took the light from the Eagle Nebula 5,700 years to get here. So we're not looking at the Eagle Nebula as it looks today. We're looking at the Eagle Nebula as it looked 5,700 years ago. And the deeper into space we look, the further back in time we go, which is really interesting if you're an astrophysicist and you're wondering how the universe was formed or what early galaxies looked like. You can find out by building more and more powerful telescopes. So as I said, this image was taken by the Hubble telescope in visible light, and that means it was in the range of the electromagnetic spectrum that we could actually see. And it's from 1995, so it's a pretty old image already. So this little chart, I'm not going to get into the cosmology of it, but it might give you an idea of how we look back in time. We're standing here in the present day, and here are the modern galaxies. So the further and further we look back in time, or the further we look with a telescope, the further back in time. We're already looking at about 13.3 billion years ago. We've seen some early galaxies all the way back there. The Big Bang is estimated to have happened 13.8 billion years ago. So right now we're looking back within 400 million years of the Big Bang. So that's how we look back. As we look back in time, we get to see what early galaxies looked like. So we stand at one end, and we literally are looking down the corridor of time as we look through our telescopes and we look at the image that the Hubble and the James Webb Space Telescope, which is the latest telescope. It's been up there about 2 years. I did a update on that last month. That's available on YouTube if you ever want to see it. One more thing I'll talk about is the electromagnetic spectrum. So energy comes in all kinds of wavelengths. The longer the wavelength, the less energy is packed into it. So we have AM radios way down on the far end of the radio, amateur radio. We have microwave oven and microwave. Infrared, which we do a lot of observations in infrared. We only see this small little sliver, and it's actually a lot smaller than that if I were to draw that to scale. We only see visible light with our eye. Everything else we need instruments to detect. Then we can go to ultraviolet, PET scan, all the way down to gamma ray flashes, and you can see how tightly those are small wavelengths. So there's more cycles per given length, and that's how the energy is packed into it. So that's the electromagnetic spectrum. So what does that really mean practically to us? Well, here's the Eagle Nebula again. The 1995 image that I showed you, taken in visible light, and then a very recent image from the Hubble Space Telescope, which I'll just call James Webb or Webb, because I don't want to say it all. But can you see the difference? The one on the left is visible light. The one on the right is what's called infrared. So that's the area of the electromagnetic spectrum just out of visible light. And what infrared does is infrared sees heat more than it does just the visible universe. So it sees right through these dust clouds to the hotter stars and the hotter areas behind. And it gives us a lot more information. When dealing with infrared, as I said, we can't see it. It's very simple when you're doing the Hubble images. You look at the wavelength of the data, and you know that between 450 and 495 nanometers is red, and if you go to 620 to 750 nanometers, I'm sorry, that's red, and blue is about 450 to 495. So between 450 and 750, that's visible light, and you just map out what hue or shade of the color it is when you're making your image. But for infrared, what you've got to do is you've got to map those frequencies that we can't see onto colors. So they usually take the highest wavelength and make it blue, and they make the longest wavelength red, and everything in between is different colors. That's how they map infrared to a visual picture that we can see. Because if you look through a telescope that just showed you infrared, you wouldn't see anything. So we have to have image specialists to map that out for us. One more image of the pillars. This was also taken with the James Webb, but it was using both of their camera, their near-infrared camera and their mid-infrared instrument. And I think this really gives you an idea of just how different wavelengths give us different information, and also gives us different beauties. You know, it's hard to imagine the full extent of the grandeur of a structure like that. The tallest column here is 4 light years long. That means it takes light 4 years just to travel from the tip to the base. Our solar system, if superimposed on this, would just be a little tiny blip there. It takes 4 light years to get to the nearest star from our sun. So that's quite a huge distance that we're talking about. So, and imagine the power that's masked by this beauty. As a birthing place for stars, what happens is in these clouds, the clouds start to collapse on their own gravity. And as the gravity pulls it together, it heats up. And if there's enough mass there, sooner or later it will start getting a nuclear fusion, and a star, a protostar, will be born. And so we're having nuclear reactions going on here. And you can see it much better if you looked on the web. But there's a bunch of little orange dots all through here, especially in this area, that are stars that have come into existence through this gravitational force. When you have a nuclear reaction, you have the radiation of the fusion trying to push the cloud out, and you have gravity trying to pull it in. And when the outward force and the inward force equalize, you have what's called hydrostatic equilibrium, and that's where the star spends most of its life. It's a stable star and lives on what they call the main sequence for most of the time until it starts running out of hydrogen, and then funny things happen, which I will talk about later on. If you look here, you'll see what looks like a lava flow, even this bright red, and these are even younger stars, protostars and very young stars, and as they're coming into existence, a lot of times they'll shoot out energy that will interact with the cloud around it, and that's what we're seeing here in the infrared. Let's take a look at the wide field view, because the pillars is only a small part of the Eagle Nebula. This is the Eagle Nebula. Do you see the pillar? Hello, hello. Oh, there we go. Here's the big one. 1, 2, 3. So that's the pillars right there. And here is a young, bright, and powerful star cluster. known as NGC 6611. And you could see that with a modest backyard telescope. Uh, the cluster is responsible for giving the nebula its other nickname, the Star Queen Nebula. And it is also responsible for casting the light upon this, upon the pillars that we see. And again, think of it, it's a number of light years, and the radiation is so powerful that it's actually illuminating that entire pillar. Matter of fact, even more so, it's blowing that pillar away. That was a cloud of gas, and it's undergoing a process called photoevaporation, where the solar wind from these stars in the cluster is actually eroding that cloud there, just like when you see the hoodoos in Bryce Canyon or different geologic features. These are the strongest parts of the cloud that have withstood the test of time, but eventually they will blow away. So just think of the amount of energy and the power required to blow something away that's about 3 light years away and to illuminate it at the same time. This entire picture here is covering about an area of 70 by 55 light years. So we're talking about a huge expanse, although from here it's just a little tiny dot. And this photographed by an amateur astronomer by the name of Patrick Cosgrove. This was taken from the Earth with, this keeps cutting out, with amateur equipment that you can buy on the market for many $1,000s, but you can still buy it as an amateur. You know, one other thing, science, to really do science, you need to always take the data that's the new data and evaluate your hypotheses and what you thought about the universe as new data comes in. You know, sometimes you hear someone say, trust the science, as that's the end of the discussion. But scientists trust scientific method in that they're always testing their hypotheses. And these pillars were thought to be about 7,000 light years away. And it's only recently, in the last 2 years, that they've determined that the pillars are only 5,700 light years away. So that's quite a difference in distance. And also, it was presumed, just a common belief, that one of the stars in that star cluster had gone supernova and had blown away the Eagle Nebula, and it no longer exists, and that it would take us another 500 years to figure out if the scientists were correct or not. But after looking at different observations through different instruments, there's a lot of question of whether that's true or not. So they're questioning their hypotheses. Now, sometimes telling someone to trust the science is a good thing. If you have a friend who believes the Earth is flat, you can definitely tell the person, trust the science, the Earth is not flat. But when it comes to cosmology, theories are always being revised. As we just sent up the James Webb. It just hit 2 years of images, and we are just surprised by the stuff that we're learning. We're learning stuff that we never imagined we'd see, and we're also seeing new data that's causing cosmologists and astronomers to re-examine their current theories. So I just started out our journey with the Eagle Nebula because I thought it was a great combination of beauty, power, and time travel, and also scientists re-examining their hypothesis and what they thought in the face of new data. I just put this map up here so you could see where it's located. Sagittarius in July and August is in that direction, so you can see this through telescopes, through small telescopes, and some of our club members have taken some really beautiful pictures of the Eagle Nebula right from here. So before we get too far out into the universe, let's go back to our own solar system for a minute. Does anyone know what kind of object that is? Yay! It's a comet. To be precise, it's comet Hale-Bopp. And that visited the Earth back in 1997. And this is a picture that I took right here in 1997 of Hale-Bopp. I got to do a little work on the image. That was back in the film days, so I just scanned this film picture. What I need to do is scan the negative and spend the time, but I'm a really lazy person, so I don't know when I'll ever get to it. But yeah, that's comet Hale-Bopp. It's a 45-second exposure that I took with a Minolta film camera, a 50mm lens, f1.2 for any nerds out there, and put it on a stationary tripod and took that picture. So the length of time it takes for a comet to circle the sun is known as the comet's period. And this comet has a period of 2,533 years. So basically that was my only chance at getting a good photo of it. Its nucleus is about 25 miles across. This is another picture that I took right here from Jenny Jump. This is actually a 4-minute exposure, which back in those days, a 4-minute exposure, if you have a camera on a tripod that doesn't move, you can go maybe 30 seconds, 45 seconds with a 50mm lens. But if you go 4 minutes, all of those stars would be blurred. So I had to have a way of tracking the Earth. I had to match the Earth's movement to get those stars to look the way they did. And I didn't have a whole lot of money for those fancy mounts back then. So what I did was I built this. This is called a Scotch mount or a barn door hinge. And basically, you can get the plans on the internet, about $10 a parts. And you look in this hinge. You look here at the North Pole. That's how you align it. So if you can see the Polaris, the North Star, through here, then you're aligned. You put your camera up here, and then there's a little crank here, and you turn it 1 rotation per minute. And what I did was I had a little radio there were no apps and no cell phones back there. That's how old I am. So I had this radio that had a time station called WWV, and it would tick out the seconds and announce each minute. It would count out 15 seconds, turn the crank a quarter turn, wait another 15 seconds, and so on. And I got those pictures. I just put it there to show you, you don't have to spend thousands and thousands of dollars to get started in astronomy. You can get a pair of binoculars, get a nice tripod, build one of these for $10, get a cheap camera, and you're on your way. And a matter of fact, that's the low risk way of starting to get into astronomy. So because you can see if you like it, if you really like staying up late and torturing your body as you take all these pictures. It's a lot less torture now that we have digital cameras. The film days were much harder, where you'd have to go, 30-minute, and you have to use a guide star so your mount. Now you can take 130 1-minute pictures, and there's software to stack them together as if you tracked for an hour, 2 hours. Some of these amateurs now, they take 3 hours worth of photographs in 1-minute increments and stack 1,000 pictures together, and the computer does it all for you, and you have an amazing picture, better than you could have gotten with the film. So we're getting much nicer pictures now with the digital age. And here's a better picture of Hale-Bopp, and it's a great picture. You can see the 2 tails. You have the ion tail, which is much lighter particles than the dust tail, and the ion tail always points directly away from the sun because the lighter particles are directly affected. The dust particles are a little heavier, so they're not affected by the solar wind to that extent. They're affected more by the motion of the comet itself. So when you see a picture of a comet, you can tell 2 things. You can tell where the sun is, or what direction the sun is in, just by following the ion tail. So the sun is right that way somewhere. And which way is the comet moving? Well, the dust tail is moved this way, so the comet is moving in this direction. down here because the dust tail is lagging back there. So anytime you look at a comet, you could tell that. Hale-Bopp was a really special comet because it was so easy to see, and the two tails were so distinct. It was amazing. Now, comets are certainly beautiful objects, but there was a comet a few years before Hale-Bopp that really displayed some frightening power. It was called Comet Schumacher-Levy 9, and it was first detected on a photograph in March of 1993 with the Schmidt telescope on Palomar Mountain in California. The magnitude of the comet was reported as magnitude 14, which is about 1,000 times dimmer than the naked eye can see. If you're a photography buff, think of your eye as a shutter speed of 1/30th of a second, and that's about how much light you take in. And you'll never see colors in nebula. It'll always be black and white. But anyway, they studied the orbit of this comet, and astronomers knew that the comet had made a really close approach to Jupiter back on July 7th of 92. And during that close approach, the unequal gravitational traction of Jupiter on each end of the comet tore it apart. It's called tidal force. It's also the moon in Jupiter is the most active volcanic moon in the solar system because it's so close to Jupiter. The tidal force just makes it go nuts, and it always has erupting volcanoes. So what Jupiter's tidal force did to this comet is it crushed it into 21 pieces. And this is a composite photograph that shows you the incoming comet, incoming towards Jupiter. So the 21 fragments slammed into Jupiter over a period of several days, centered around July 19th, 1994. A really cool time to be an amateur astronomer, although it actually slammed on the other side and you had to wait for Jupiter to rotate that into view. They hit Jupiter at a speed of about 36 miles per second, causing plumes of smoke, thousands of kilometers high. I shouldn't say smoke, just plumes thousands of kilometers high. They left hot bubbles of gas in the atmosphere and great dark scars, which you see right here, that lasted for months. The largest fragments of the comet were estimated about 2 kilometers wide, so that's 1.6 miles. But the scars you see in Jupiter that these fragments left, the largest ones are larger than Earth. They left humongous scars that lasted. So that gives you an idea of Earth versus Jupiter, because Earth's about the size, that's about the size of Earth. So just amazing. Jupiter has been called a cosmic vacuum cleaner because a lot of times it protects the Earth by perturbing the orbits of incoming objects that are coming into the inner solar system. It's our friend. So this was the first time that humans ever saw objects collide outside of Earth, but within the solar system. And of course, scientists got a fancy name. They called it an extraterrestrial collision of solar system objects. The first time we ever witnessed that. Okay, now we're going to talk about some beautiful things that are left behind by dying stars. And I do a talk on the life and death of stars. I'm not going to go deep into this. But just quickly, so you can understand where I'm going with this, we saw that dust clouds in the Eagle Nebula collapsed and then started to fuse hydrogen, and we had nuclear reactions. That's the birth of a star. So an average star like our sun, up to about 6 or 8 times the size of our sun, will take this top path. And I'll show you this chart again later. After it's done burning up all the hydrogen, fusing helium into oxygen and carbon, and pretty soon gravity loses out and and the outer shell of our sun will just get bigger and bigger as it becomes a red giant, kind of like Betelgeuse. And at that point, which is about 4.5, 5 billion years from now, Earth will be inside, Mars will be inside of the sun when it becomes a red giant. Slowly but surely, the outer shell, about half of the mass of the sun, will drift out and will become a planetary nebula. And the rest of the material, about half of the mass of the sun, will turn into a white dwarf. It will no longer be fusing hydrogen or any of the elements, but it'll take billions of years to cool down, and that'll be surrounded by the planetary nebula for about 20,000 years, and then the planetary nebula will disperse, and we'll just have a white dwarf left behind. So if you're around about 5 billion years, that's what you can expect. If the collision with Andromeda in 4.5 billion years doesn't mess us up too much to start with. So it leaves behind these planetary nebulas, and they're not planets. They're called planetary nebulas because the first people to discover them saw that they looked round like a planet, not a point of light like a star. And they saw that it was a diffuse object, which is a nebula. So they called them planetary nebulas because with the low technology of like telescopes like Galileo's on a few years after time of Charles Messier in the 1700s, they called them that just to differentiate them. So planetary nebulas, this is like a typical planetary nebula. This is called M57, the Ring Nebula, and you might be fortunate to see it tonight. When you go out, you look straight up, and there's a star Vega in the constellation of Lyra, and you will see the Ring Nebula is right there. And these guys in the telescope shacks love to point towards it. Again, your eye's not going to see any kind of colors. Your eye will see like a cloudy smoke ring, like someone just a little smoke ring, and it's going to be very tiny. And in the middle of that is a white dwarf. And this up to this presentation, I had been showing a visible light photograph of the Ring Nebula. It was also on the first thing that you saw on the on my presentation. This is an infrared shot that just came out of the James Webb, and it gives so much detail. It's amazing. This, you could almost see the shock wave here of all these filaments, and that actually that was in the first red giant stage before it collapsed and then went out again. So this was about this red was probably about 20,000 years before you had the ring that you could see with visible light. This is what you can see in visible light. That's what Hubble could see, and this you need infrared to see the traces of the heat left behind. There's a 15th magnitude star in the middle, the white dwarf, that's no longer powered by nuclear fusion, but it's super high density. And this ring is about 1 light year wide. And in 30,000 years, the only thing that'll be left is the white dwarf. The white packs half of the mass of our sun in an area the size of the Earth. So it's super, super dense. It's like a couple metric tons if you could pick up a teaspoon of that material of a white dwarf. So it's very, very compact. And we'll see stuff that's even more compact. So I'm just going to go through a couple of these to give you an idea. That one's called the Hubble Spirograph. That was taken in 2000 from Hubble. Its official name is IC418, but I like Hubble Spirograph a lot better. It glows with these multifaceted, intricate pattern. It's just gorgeous. It's about 2,000 light years away from us in the direction of the constellation Lepus. This planetary nebula qualifies as a strange object. It's called the Cat's Eye Nebula, and it's got astrophysicists stumped as to how these rings occurred. This is highly unusual. And these aren't actually rings, they're bubbles around the whole thing. We're looking at it like you cut an onion in half and you'd see these rings. There's at least 11 rings, and it looks like they were created in 1500 year periods. And there's a whole bunch of different theories, but nobody knows for sure how this came about. But it is a very intricate planetary nebula. One last planetary nebula that I really like. This is called the Butterfly Nebula, and this is found in Scorpius, which is that way towards Sagittarius as well. It's known as a bipolar nebula, not because of its mental health, but because we see two different poles shooting out here. It's one of the most complex structures observed in a planetary nebula. It doesn't even look like a planetary nebula. And although it looks beautiful, there is tremendous power in this. The spectrum of its center star shows it to be one of the hottest stars known in our galaxy, with a surface temperature of 100,000 degrees Fahrenheit. Compare that to about 10,000 degrees Fahrenheit for our sun. So it's 40 times hotter. It must have been a big star. It's estimated to be that it was about 5 times the size of the sun. So it was approaching the limit before it would be a star that it would end up as a supernova. But it still ended up as a planetary nebula. And it's only about 64% of the mass of our sun, which is about what happens to those. Our sun will be about 50% of the mass in its star, in its white dwarf. So the central thing, because it's hit a hello. Let me see what's going on here. Hello. Okay. That's always the speaker. Okay. So the central star itself can't be seen because it's surrounded by that donut-shaped ring dust, which appears as just a dark band in this picture. And it seems like it's pinching the nebula, which is why we see the bipolar jet. We see that astronomers feel that this torus, and torus is the fancy name for the donut-shaped ring of dust. The torus is the cause of the bipolar shape. The wingspan of this butterfly covers about 3 light years, and in reality, it's not really a delicate wing of a butterfly. It's a roiling cauldron of gas heated to about 36,000 degrees Fahrenheit, and it's racing across space at about 600,000 miles per hour, every day. 600,000 miles per hour. That means it could go from the Earth to the moon in about 23 minutes. It's moving. It's getting bigger and bigger. Although, obviously, at the distance, it's awful hard to measure that unless you have the kind of instruments that NASA has. This nebula is about 4,000 light years away from us, and the image was taken with Hubble in 2009. I used to display the original Hubble image from 2009. Just recently, about a year ago, they reworked this the image. They used the same data, but a lot of advancements in software over the last 15 years, and they pulled a lot more detail out of the same image, out of the same data that Hubble had given us. And I just think this is one of my favorite planetary nebulas. It's just amazing. A different class of object is known as a reflection nebula, which is a cloud of molecular hydrogen and dust that's illuminated by a star. It reflects the star's light. That's why they call it a reflection nebula. And the Pleiades, which is one of the things that got me started in astronomy as a Boy Scout. When I looked up, I used to think it was a little dipper, because it kind of looks like a dipper if you look at it. It's in the winter sky, and it's one of the most famous emission nebulas out there. It's called M45 from the Messier catalog. The Pleiades, the Seven Sisters. In Japanese, it's called Subaru. And if you look in the Subarus, you will see 6 stars, not 7. And apparently they left the 7th star off because there was one blind sister. That's what I hear. But Subaru is definitely the Pleiades. And so if you own a Subaru, now you know what it was named after. This has actually the open cluster is about 3,000 stars in the cluster. You can see the main stars are much brighter. It's about 400 light years from us, which is pretty close, and it's one of the closest clusters to the Earth. And if you see it in the winter sky on a cold, crisp night, it's just breathtaking. It's such a beautiful jewel, and if you have binoculars, it's amazing. Originally, astronomers thought that the stars in the Pleiades were illuminating some of the dust that was left over from when they were born. But the current thinking now is that it's going through an unrelated dust cloud at the speed of about 18 kilometers per second relative to the cluster. So now they're thinking it just happens to be superimposed, and these stars are lighting up the dust cloud, and we'll keep moving on. Okay, so we looked at the remnants from a star about the size of our sun. What happens if it's a bigger star? Well, if it's a real massive star, greater than 8 times the mass, up to, it really depends on the circumstances, but 40 to 60 times the size of the sun. They'll all become red supergiants, but they will keep fusing elements until they get to iron. Iron is the first element that requires energy. It doesn't give off any energy. So as soon as iron hits the core of a star, within seconds, the star just implodes and becomes a supernova. And a supernova is such a bright explosion, it can outshine the entire galaxy that it's in, billions of stars. It's quite the scene. And for the star that's up to about 60 solar masses, it'll go this way. It'll become a neutron star. If it's larger than that, it goes right to being a black hole. And we're going to take a look at both of those, starting with the neutron star. Here's just a picture of the core implosion. This is an artist's interpretation of what happens. You got the red giant. All of a sudden, there's carbon in the core. Supernova explosion. You're left with a supernova remnant and a neutron star in there. Let's see how we're doing here. Okay. So here's a photo of one of the most well-known neutron star supernova remnants. It's called the Crab Nebula, or M1. This is a mosaic image taken by Hubble in invisible light. It's about 6 light years wide, and again, it's the remnant of a star's supernova explosion. This photograph is from 2005. What I really think is cool when I look at this in my telescope, I think of this supernova happened around the year 1054, and there were Japanese and Chinese astronomers that recorded this event. They saw the supernova in the sky as a bright star. They saw it during the daytime. It was so bright that they could see this star in the daytime and recorded it. And we have their notes on that, which is just amazing to think. 1,000 years ago, as I'm looking up, 1,000 years ago, there were people on this planet who actually saw this thing as it exploded and saw it in pure daylight. Now it's magnitude 8.4, and there's a rapidly spinning neutron star embedded in the center of this nebula. It's the dynamo that's powering. It's the energy from that neutron star that's illuminating this entire this entire 6 light-year wide nebula. The bluish light comes from the electrons whirling at nearly the speed of light around magnetic field lines from the neutron star. Very heavy magnetic lines in a neutron star. There's some neutron stars called magnetars that are so powerful that if you were within 1,000 miles of it, it would rip you apart. It would rip the atoms in your body apart. That's how powerful the magnetic fields are. Neutron star is like a lighthouse. It's emitting these relativistic jets, twin beams of a lighthouse. So it's spinning around, and we call it a pulsar because as it rotates 30 times a second, we can see those pulses. We can pick them up in radio telescopes. And again, the neutron star is crushed ultra dense core of the exploded star. It's even more dense than a white dwarf. It's actually the gravity in there. You can watch this on YouTube. There's some great neutron star videos. The pressure that the electrons and protons are squished together to make neutrons, and so the only thing in the core of this neutron star is like this neutron fluid or jello that's there. It's amazingly dense. Besides a black hole, there's nothing denser. This is another nice view of the Crab Nebula. This is more recent. This was released October of 2023. It's from the James Webb Space Telescope, and it's a combination of both the near and mid-infrared instruments on that telescope. And NASA notes that the white material is synchrotron radiation, which is emitted across the magnetic spectrum, but becomes particularly vibrant thanks to the Webb's sensitivity and spatial resolution. It is generated by particles accelerated to extremely high speeds as they wind around the magnetic field lines of the neutron star. It's the power in this neutron star is, I can't imagine it. It's unbelievable. Also, the neutron star itself is right in here. And there's other wisps in there. Again, all of this, the wisps and the clouds are all affected by the magnetic field lines of the neutron star. Okay, let's look at black holes. So if it's a really, really, really big star, it's going to end up as a black hole. And this is an artist's rendition of a black hole. We can't see black holes, right? There's something called an event horizon, and if you pass the event horizon, not even light can escape from a black hole. We can see their effect in a number of different ways, which we're going to look at. Black holes are so massive, they bend the very fabric of space and time. And Einstein predicted this before we knew that they actually existed, and now we know that they do. And a lot of the things he predicted, like gravitational lensing, which we're going to look at, also exist. Amazing that someone who is so theoretical can predict things that we actually prove years later when we have the instruments that are sensitive enough to prove it. A black hole so massive, its gravity will cause matter to fall into it. And so although it's not possible to see a black hole, we can see the area just outside that event horizon called the accretion disk. And the accretion disk is where it's eating up. If it gets close to a star or a lot of mass, the mass will start to spin around the black hole, and as the black hole gobbles it up, and then it falls into the event horizon and we don't see it. We have this telescope that's a very large array. Right now I think there's 3 components in the US, Mexico, and Spain. It's called the Event Horizon Telescope. And we were able to image, back in April of 2017, the accretion disk of this black hole, 55 million light years from Earth. And what you're really looking at is a silhouette of the black hole's gravity. You're looking at the accretion disk as it's sucking up matter. You can see the imprint of the black hole. Now, another phenomenon that Einstein predicted that I just mentioned was gravitational lensing. And again, that's very massive objects alter the very fabric of space-time. Think of a piece of fabric and you pulling down on it to make a cone. The path that light will take will go actually around the object. Best thing to do is to show you. And this is another new picture. I used different pictures before from Hubble. This is a James Webb photograph in the near infrared, taken in April 2023. And it shows a gravitational lens caused by the galaxy cluster located about 6.3 billion light years from Earth in the constellation Coma Berenices. The lens that the gravitational lens is the light that goes through the gravitational lens is greatly magnified. And so scientists can not only see stuff behind massive objects, but they can also see things that are magnified. And here, this is called the Great Seahorse Galaxy, and it actually is behind this massive cluster. And what happens is this bends space-time so that the light travels around and comes out the side, but very distorted. These are galaxies as well. You can see this is what a normal galaxy looks like. You see this one, this one, this one. The redder something is, the further away it is. But when a galaxy goes through a gravitational lens, it gets very distorted, but it also gets magnified. So scientists can learn something about stellar evolution by looking at these very distant galaxies that are being magnified by gravitational lenses. It's just amazing. When we first sent Hubble, we used to point it to blank areas in the sky, and we were just amazed at all the galaxies that were there where we had no idea they were there. Now we point it towards crowded areas, and we see these massive clusters magnifying and lensing the objects behind it. And it's another way of looking at it. One last thing that Einstein predicted, and that we have seen a number of times, this is called an Einstein cross. The massive galaxy that's doing the gravitational lensing is right here, and behind it is a quasar, which is a supermassive black hole in the center of a galaxy. This is one quasar, but it has found 4 different light paths to go around this supermassive galaxy group here, and they've called this the Einstein cross. So that's one object that we're seeing come through 4 different light paths. Just amazing. And finally, I will leave you with one last gravitational lensing photo. This one's called Gravity's Grin, also the Cheshire Cat galaxy group. This was imaged with both the Hubble and the X-ray instrument on the Chandra X-ray satellite. The arcs are the gravitationally lensed galaxies that outline the face, and the 2 eyes are 2 galaxies that are colliding. Their collisional speed is about 1,350 kilometers per second, and it heats gas to 1,000,000 of degrees, and that's why we see all that purple haze. Is the X-ray instrument is recording that X-ray glow shown in the purple hues. This Cheshire Cat group grins in the constellation Ursa Major, which also holds the Big Dipper. and it's about 4.6 billion light years away. And that's my last image of tonight. Thank you all for your attention.
All right. Thank you, Walt, for another great presentation. Thank you all for joining us. So we are having a question and answer session because I'm sure there are people with questions. I know online had a number of questions. But before we get into question and answer session, I will go over the safety briefing again because I did see a couple of you sneaking in, and you must know this information. With that being said, we have the restroom, the porta potty in back if you need to use the restroom. It is illuminated by red for ease of seeing. We also have a little museum area and gift shop, which I will be manning after the question and answer session. When we are leaving, we are using headlights. We do not want to get run over. We do not want to see people get run over, nor fill out paperwork or pay medical bills for getting run over. Let's not do that. If we're using flashlights, do keep them pointed towards the ground because we do not need to blind each other. The only one who should really be completely night blind is me because I'm monitoring chat and looking at my phone constantly. It's a hazard of what I do. We do have, I believe, a number of observatories open with the roll-off roof. Each should be and a couple of our volunteers have their own telescope setups on the lawn. Feel free to go up to the volunteer who is running them and ask what they're viewing through the telescope. Many of them will tell you, here, let's take a look, and tell you all about what they're doing. Do listen to their directions with that. So how question and answer works. Like I said, I'm a bit night blind, and it is very dark. So people here, you get to raise your hand and wave it about like you just don't care. And don't put it down because until I get to you, I'll lose you. Because, again, night blind, you're all kind of shapes in the dark. Online chat, you get the easy part, just type. So I'm going to start out with this hand over here.
Hello.
Hi.
So you're saying distance is relative to time, right? So when you're looking at these galaxies and we're talking about loopholes and this and that, we could basically travel faster to those, just we don't know how to, right?
I'm not sure I'm following you there.
Okay, so
I mean, there's theories that a black hole might lead into a tunnel that will spit, and a white hole will spit you out the other side.
or loopholes or whatever we want to call them, wormholes.
Wormholes, yeah.
I'm sorry, but it could like you estimate a distance, but it might not be that distance in space.
No, it would be that distance. Yeah. We measure redshift as when we're going that far out. What some of these loopholes, wormholes, and that theory is there's like multiverse, and sometimes galaxy may curve in on itself. But when you measure the distance, it's fairly reliable distance. I mean, we're like good scientists; they're always revising how far they think something is because they get better data. But they have a pretty good calibration as far as we can see that.
Right. So our first online question was, if there was one interstellar object you could visit, what would it be?
Oh my goodness. You know, I do like the Eagle Nebula. It's always been one of my favorites, so I guess I'll go with that.
Right. Our online viewer had also said that if a Dyson sphere existed, he would like to see one of those.
Well, the closest that was postulated for a star called Tabby's star because of the weird variability in light, but it's been disproven by Tabby herself, the discoverer of the star.
All right, we got a question over here.
How far away is the closest black hole to Earth?
It's at the center of our galaxy. It's called Sagittarius A. Most galaxies have massive black holes at the center. That's a great question. And
Do
so
you know how far away it is, though?
it would be about 20. I'm guessing about 25,000 light years would be my guess. The entire Milky Way galaxy is 100,000 light years end to end. That's the size of our galaxy. We're on one of the arms, and we're looking in. When you look towards Sagittarius, which you can see later on, if you walk that way, ask someone to, it's like a tea kettle looking thing. When you're looking at Sagittarius, you're looking towards the center of our galaxy, and hence the center, the black hole at the center, which is why it's named Sagittarius, because we find it in that constellation.
All right. So our next online question: would you ever try and do film astrophotography again?
No. No. It's you know, there's a comeback in film photography for street photography and stuff. That's great, but digital cameras now, as far as what you can do with them in astrophotography, it's just, you'd have to have a really strong yearning for nostalgia and maybe even a little sadomasochism to go back to film.
All right. Oh, I see one over there.
What's a comet?
A comet is a dirty snowball. There's a cloud out by Neptune and Pluto, where there's a lot of debris, and what happens is they get their orbit get perturbed, and they come towards the sun. The closer they get to the sun, the more the ice melts and sublimates into gas, and those are the tails that you see, the dust and the gas are coming off of it as it comes to the sun. The tails always point away from the sun because the solar wind blows. They go around the sun and then they go back out. Almost all of them have their origins in the solar system, but just recently we found a comet that had an orbit that was parabolic. So it came in from outside our solar system, swung around the sun, and then left our solar system. We've seen 2 of those so far. There probably been more, but we just they're hard to identify. You gotta go fast, watch fast.
All right. We got another question here.
Thanks. So I have 2 questions. One is the onion ringed one.
Cat's eye?
The onion ringed one, that the one with the onion peels that you showed.
Yeah.
What are those peels made of? That's one question. And the other is the dust that we see around the nebula. Are those dust from the planets that have been sucked in by the collapsing sun?
There's a lot of interstellar dust out there, and you know, some of it comes, you know, in the thick cloud. You could actually get a field where stars are being born, like the Eagle Nebula or the Orion Nebula, or Carina, the cliffs of Carina. So yeah, some of that can be garbage, like the asteroid belt, you know, crushed rock, but a lot of it is just very fine gas and dust. And your first question was what the
rings in the
oh,
one that
the
looked like
gas.
an onion.
They are made. Think of our sun. After it expands into a red giant, half of the mass of our sun becomes that white dwarf. The other half becomes the gas that we see. So the mystery with the Cat's Nebula is it wasn't just a big cloud of dust that just drifted away. It looks like it had 1,500-year pulses that made those rings. And scientists are wondering, you know, is it a magnetic field that made that? Did it actually pulse the matter out somehow? They're still wondering about that one. That's the real mystery, is why are there rings that look like they're 1,500 years apart rather than just one big cloud that was made and then is going to scatter.
All right. So our next online question: what is your favorite object to look at in the sky? And if you still do astrophotography, what is your favorite object to photograph?
Well, my favorite object there's so many objects to look at the sky. You know, I really like showing the sky to younger people. I do these talks in the hope that some young students will take a look on the web and take a look at the science. You know, it's a lot of fun to read science fiction, watch science fiction movies, but this stuff is real. And so I just love showing the sky. I love showing Saturn. Hello? Yeah. Showing Saturn or Jupiter to someone, especially a kid, for the first time, because it's just such an amazing sight. It looks surreal. And so I love that. Nebulas are a lot of fun to photograph, but if you're looking in a telescope, they all look like white, cloudy objects. And if you look at a lot of coffee table books and picture books, you might even be a little disappointed by some of the nebula. But when you look at Jupiter and you watch one of its moons go behind it and blink out, or you see a moon passing in front of Jupiter and you can see the shadow crossing Jupiter, that's just amazing. And no matter who you show that to, and that's a lot of fun.
All right, online chat, if you have questions, do get those in. I want to make sure you guys have plenty of time to get any questions you have in. I like to say that because stream delay is a thing, and by the time they actually hear that message, we're already a couple minutes into the future. Time travel. Was there any more questions here? Perfect.
Where was our sun born?
It was in the Milky Way, but it's a tough question to answer because the Milky Way's arms are revolving just as we're going around the sun. Our whole solar system in the Sagittarius arm is going around. So it was born somewhere in the Milky Way, but you'd have to do a regression based on how fast those arms are moving and where exactly that position would be in a map of the galaxy.
It doesn't help that everything's always constantly moving.
Everything's moving
spiraling.
in 3 or 4 different ways.
It's like one of the spinning battle tops you get where it's like, woo. Any more questions? I hear a lot of crickets. And I see vague humanoid forms in the dark. All right, so our next online question. What kind of telescope do you have? You still have a telescope, right?
I do, yeah. I like taking pictures with a wide field camera too, and trying my hand at landscape photography, where you take a picture of the Milky Way over landscape. But I have a 8-inch catadioptic telescope, Meade. I also have an astrophysics Traveler. It's a 4-inch refractive telescope. So I have a reflector and I have a refractor. I also have one that my son made when he was 10 in the basement, but I don't use it anymore. It's a Dobsonian.
I'm afraid to ask what the price tag on that astrophysics was.
Yeah. My wife may be listening. I better shut up.
Right, we got another question here.
Just wondering, how old is our sun?
Our sun's about 4.5 billion years old. It's halfway through its life. It's an average life star that has an average life of about 10 billion. The big blue stars, they could have a lifespan as short as like 60 million years. They burn out very quickly. But ours is as steady as she goes. And some of the dwarfs, like a brown dwarf, we think could last trillions of years. But since the universe is only 13.8 billion years old, we really don't know how long they'd last for sure.
All right, we got another one here.
What kind of camera gear do you use?
What kind of camera gear do you use?
I use I have a modified Canon Rebel. I say modified because I had the filter that takes out the infrared light taken out, and so I get better hydrogen alpha shots. I get I get more red in my nebula. But you can start with just any camera. Canons are good because they don't have a lot of they have less heat on their sensor. But the best way to get started is to get a camera that you're familiar with. Put like a wide angle lens, put it down in a field or put it in front of a barn where it's kind of pretty, and just try your hand at taking shots of 45 seconds to a minute at ASA 1600 or 3200. And if you want to really get adventuresome, take a flashlight and paint the front of the barn, or the tree. You can shine a light and just go back and forth, and it'll really pop out nice. And so you'll have a bright tree or a bright barn with a Milky Way in the back. There's also a great app called the Photo Peels, PILS, that will tell you where the Milky Way is going to rise in any area that you want. What's good to take photographs of. But just start easy. Don't try to take like a telescope and try to get like the Eagle Nebula, because it'll be frustrating. Just start taking some nice landscape pictures with a star field above it, and work your way from there.
If you know how to write script, you can get fancy with it and write messages on the side of the barn.
There you go. Aliens.
That for any of the astrophotographers, that's an idea. If you have a significant other you need to propose to, you could laser like, "Will you marry me?" on the side of the thing.
Is that how Chris proposed?
No,
Okay, just wondering.
no. It was, "Hey, I feel like we should get engaged." I'm like, "Yeah, I feel like that should be a thing too." And then we were engaged. Very simple. All right. Were there any more last minute questions? All right. So thank you all for joining us. Do have a great night. Like I said, if you're online or you go online later, do hit those like and subscribe buttons or the follow button. They're all free actions. Let us know that we're doing a good job, and allows us to know that there are people who still want to see this content. Like I said, all this information and more is available on our website, uacnj.com, as well as you have access to us on our social media, our Facebook, our Instagram. We have our Discord channel. And with that, everyone have a great night. And until next time, clear skies and good seeing.
Yeah, have fun. Don't be shy.